It's like this. Okay, it's coming down. Come on. Home. Okay, here we go. And the university spend a lot of money to hire the IT guy, but whenever there's the IT issue, ask them to help, they will never show up until the end of the earth. So online student, I hope you can comply this issue with the university. In-class student, they don't have this worry. If you do not comply, they never fix the issue. Where's others? Got flushed away by the water or something? We should save them. All of this recipe got flushed away into the river or whatever. It's gator inside. Okay, so let's wait for 1 more minute. And we're going to start our class exactly at 12. Okay, start. So last time, we ended with the water phase diagram. Yes. So we mentioned about the Gibbs rule of the phases, and we draw a phase diagram of water, remember? This is something like this. So this is the P, this is the P, okay? So something like this. Okay, and then this one is in the gas phase, this is liquid phase, this is solid phase. Okay, so you can see what it tells us. It tells us as the temperature goes up, okay, when the pressure is high, we can change the solid to liquid, okay? And when the pressure is low, we can change solid directly into gas, okay? Of course, the gas can change into liquid, okay? And of course, we have one unique point we call the trickle point that the three phases get equilibrium to each other. Okay? But at the beginning of class, we mentioned about phase transition. The driving force of the phase transition and the constant T and P is the Gibbs free energy. Right? We want to minimize the Gibbs free energy. Then we trigger the phase transition. Okay? And we know this figure, right? So this is the D, this is the G, the Gibbs free energy. We know that it's going down and going down. And for example, this one is the liquid phase, this is solid phase, okay? Then we have the phase transition at this point, okay? And this one is the melting point. The question is, how can we get this phase diagram from this GT chart, okay? So basically this one is the projection of the GT chart on the two-dimensional place, okay? I will try my best to show you how can we get it. How can we get this phase diagram? I'm trying my best, okay? I'm bad at drawing. I'm looking for online to find a picture, but I cannot. I'm asking the ChatGPT or Gemini to give me that. They cannot. Okay, if there's no online resource, they cannot. Okay, anyway, so, but you can find part of the drawing on your textbook. Okay. But it's not the entire one. Okay. All right. So we have the y-axis is the G, of course. Okay. And we have the P on this direction. Okay, this direction P goes up. P increases along this direction. Okay? Then this way, and this way. Okay, and along this direction is the T. Okay, right now we have the three-dimensional this diagram. Okay, we know that if we can only consider closed system. Okay, right now we only consider closed system. Closed system means that the particle number doesn't change, right? Then we don't need to consider the chemical potential. We only consider G as a function of P and T. Okay? So we can draw it there. So to make the drawing more, make the drawing clearer, we can make this make a cube. Into the cube. This is basically I just copied the idea from textbook. I just want to make it rich to show you more details. Okay. All right. So let's first of all consider the solid. Okay. Consider the solid phase. We know that as the temperature goes up, think about at this point. Okay. No, probably at this point. Remember that at this point, as the this is solid, okay? This is the solid, the Gibbs free energy of solid. So as the temperature goes up, how the Gibbs free energy change? How the Gibbs free energy change as the temperature goes up?
Up, down.
Yeah, okay. All right. So that means along this direction, it should going down like this. On this point, okay, on this point it's going down. Let's make it easier. If there are so many curves, we just make the job so complicated. Just make it flat. Okay. Something like this. Going down, okay? This is solid. And as the pressure goes up, how the Gibbs free energy go? Going up, right? As the pressure goes up, the free energy goes up, okay? Because dG is proportional to VdP. Correct? Pressure goes up. Like this, okay? And on the high pressure part, the same thing as the temperature going up, it's going down, and then we form this point, okay? This is the three-dimensional Gibbs free energy of the solid, okay? We know this is solid line, this one is solid line, this is solid, this is solid. Correct? Because I mean, G depends on P and T have two-dimensional structures, right? Okay. So when the temperature is really low, what about liquid? The Gibbs free energy of liquid is higher or lower?
When the temperature is high?
When the temperature is low.
When the temperature is low, Gibbs free energy is low.
No. For the liquid, it's higher than solid or lower than solid. At this temperature, this is Gibbs free energy of the
Low.
sure. The liquid is here. So that means at the low temperature, liquid is stable state. Are you sure? Is it solid or liquid at low temperature? Solid, right?
Solid.
It should be here, right? But we know that we have phase transition, so the curve should look like something like this, right? Should be something like this, correct? It's going down.
Going down less than the solid.
Huh?
It could be.
What?
It is coming down, more down. or-
Yeah, because when the temperature goes up, it's changed to liquid. Right? You have phase transition.
But it is crossing the line of the solid.
Huh?
It is crossing the line of the solid.
Of course, because they have phase transition, right?
Oh, okay.
We mentioned this one last time, right?
Okay.
Because they have phase transition,
Oh.
then you have this is the melting point, right?
Mhm.
So we just draw it something like this. So we can make it probably like 6 to something like this. It's still good. Okay. And then, okay, at this one, okay. So how it evolves? At high pressure, at high pressure, okay? At high pressure, okay? When the pressure goes up, can we solidify the liquid? If we compress the liquid, it will solidify, right? So at this point, which is the where is the chemical potential of the liquid, or the Gibbs free energy liquid? Is here or here?
Lower.
Huh?
Below that.
Huh?
As pressure goes up, it'll be below that plane.
I mean, it's hard to tell. It's hard to tell because it really depends. Okay, it's kind. I mean, in our general opinion, when pressed, liquid can be solidified. But sometimes not the case. Okay. For example, right now we are trying to build the diagram of the water. Water is very strange.
Yeah.
We press it, it's melt. Okay. So we just talk about the water. Okay. So that means you got the pressure, the chemical potential energy of liquid is lower than solid. Okay. This is really, really weird. But we just try to demonstrate how we build that phase diagram of the water, okay? You can see that this is solid, this one, okay? You can see the line have the negative slope, okay? For regular one, it's have positive, but this one negative. Okay, that means if you pressurize it, if you increase at a certain temperature, if you press the water, it changes from solid to liquid. Okay, that's the reason when you freeze the water, the volume expands. Okay. Anyway, okay. So and then on this way, it also goes in this way. It goes in this way. Okay, goes in that way. Okay, and you can see. Let me change this line to dashed line. You can know that it's underneath. Okay. All right, it's clear. Then you can see we have two planes, right? One is a heat-free energy of the liquid, the other is, this one is liquid, the other is solid. Then you can see these two planes has the cross line, right? The cross line is here, just leave this line. Correct? This is the line where these two planes got cross, right? Then we do the projection here. And then the projection of this point and this point, the line linked these 2 points have this line, correct? And under here, you can see the free energy. Which one free energy has lower free energy? This one is liquid. This one is solid. Which one have the lower free energy? The solid, right? This is liquid. This is solid. Solid has lower free energy. Right? The free energy plane of solid energies, the free energy plane of the liquid. Right? Is that correct, everybody? And this area is what? This area is solid. Okay? And the other half, this one is liquid. Correct? And this is we got the phase diagram. Basically, this line is this line. This line here. Okay? Is that clear? We have two planes. One free energy is like this. The other free energy just cut through this line this way. So we have the cross line here. The projection of the cross line on the PT plane is a phase boundary. Okay? Is that clear? Okay, so what about these two curves? That's very challenging. Let me try my best to join it, okay? In order to join, let me remove this line first. I want to make it as clear as possible to demonstrate how what the three-dimensional structure looks like. Somebody have the marker pen with different color. Where's the marker pen? Okay. And we know this one is a solid line. This one is a liquid line. Okay, this is a liquid line. Okay, this is liquid, that is solid. No, sorry. So, yeah. Let me try to drop this down. I want to what I'm drawing is not necessarily physically or mathematically precise or strict. Just give you a demonstration. All right. These two planes just cross each other. Okay, so what's the liquid looks like? What's the liquid look like? Liquid, give me a second. Let me try to move this one further down. Let me try to move the, give you more space to draw this diagram. We still have this frame here. Okay, I just give more space here, so we have enough space to draw the chemical potential of the okay. Let me extend it. Okay. So for the water, okay, so this is temperature. This is the temperature, okay. For the gas, at high temperature, the chemical potential of the Gibbs free energy of gas would be the lowest, right? And at the lower temperature, it should be the highest, right? So for the gas phase, it should be something like, give me a second. Let's see, gas. Not really. We are trying to build the. Okay, let's assume that the pressure very low. Okay, but think about it. So at the low temperature, it should be gas. But at the high temperature, at low temperature, although if the pressure very high, it definitely becomes solid or liquid, right? But if the pressure very low, for example, we put the ice in the vacuum, it's still vaporized. Okay. So we are not talking about something extremely low. Okay, we're talking about something probably around 94 or 5. So just talking about this area. Okay, just talking about that means the gas phase still exists in this area. So that means the gas is here, okay? The gas is here, so it's going down that way. Okay, this is gas phase. This one is gas phase. Okay, we'll make it wider. And as the pressure goes up, the gas phase, the free energy of gas going up very quickly, something like this, okay? And then it's going down in this direction, okay? And then this line dropping behind. Okay, this one comes behind it. And then we need to link these two lines to these 2 points. It's go down here, and then it's go under. Correct? I have no idea whether you can see these 3 lines. Okay, right now we have 3 surfaces. Right, we have 3 surfaces. Correct? We have 3 surfaces. Any questions so far? All right.
So here, solid point is in between the gas and liquid.
Which solid line?
In that exists, in the middle exists.
In the middle, which one? Can I come here to point out?
This one.
No. This is just the axis.
Here is the solid, right? Point.
This one is gas. Okay. And this one, yes, this one is solid. This one is liquid.
So solid is in between.
Yeah, in between. Okay.
Liquid is the middle phase.
Yeah, it's fine. Okay, so right now we have several. You can see that right now we have several cross lines, right? From the liquid to the this is the liquid and the liquid and the solid. We have one cross line here, right? And for the liquid and the gas, okay, for the liquid and gas, this is the liquid. This is gas. The one point is here, and liquid and gas. This is liquid. This is gas. Another one is here. Correct, everybody? Yeah, another one is there. Then we have another cross line here. Right? We have another cross line here. And another cross line here. Something like this. Okay? And then, wait a second. Let me see. There's something wrong. Yeah, when I'm drawing this 3D, I also myself got confused. There are so many lines. I think that's the reason I'm looking for online. There has beautiful drawing, but unfortunately I cannot find. Probably if you know, can just share with me. Give me a second. Let me check. Okay. Be patient. The liquid. This one is liquid. Okay. Let me check. This one is liquid. That one is gas. Oh, I see. There's probably something wrong. Solid. And this one is liquid gas, and liquid gas right here, and liquid. Oh yeah, there's something wrong. This one is the liquid. This one is solid and gas. Or this solid and gas. This one is solid and gas. So it should be something here. Solid and gas. Yes. Here we go. We have one line here. This is one line. And the other is the solid and liquid, yes. And I mean, basically all these three lines should cross the same point, correct? If you have 3 points, they always cross. I mean, you have basically, you have the 3 lines. All the 3 lines will go through the same point, correct, everybody? If you have 3 points and they just cross each other, you can always find this cross line will go through a single point, correct, everybody? And the projection of this point basically is the triple point. Okay, this one is a triple point. That means you have the solid liquid and the solid liquid and the gas phase can coexist. Okay, and the projection of this line is this one. The projection of the solid and the liquid line is here, and the projection of the gas and solid line. The projection of gas and solid line is here. Okay? And the projection of the liquid and gas line. This one is liquid gas line is here. And the liquid gas line is somewhere. Liquid gas line should be somewhere. Somewhere. Anyway, so it should be somewhere here. Okay? So all these 3 lines have to cross each other. But you can see that for this part, so this one has the lowest energy. So this one has the lowest energy. So this one should be solid, and then the entire this area is gas because they have the gas have the lowest energy on this area, and all this one is liquid. Okay. But you can see this line goes to this area, right? But actually, the cross of this line, where's the project? The cross of this line actually is above. This line is above the gas phase, right? The liquid is above the liquid phase. So liquid phase is stable. Then this line actually doesn't exist, or metastable state. Okay, and this one the same thing. The solid and gas line actually solid gas line is this one. Actually, is above the gas line, so this part disappeared. Okay, and the same argument. This part disappeared. Okay, it's a metastable state, and this one the same argument. Okay, because this is a metastable state. Then we have this kind of the projection of this cross sections, cross line, whatever. So it's formed the phase diagram on the PT chart. Okay. It's complicated. I'm trying my best to draw the picture, okay? So I hope you appreciate my good hand drawing. But anyway, so this is basically the argument, okay? Because but if we put a lot of lines, it becomes very complicated. So you can see that I'm trying my best. I draw this picture on my, this is my probably the 5th slide, okay? But anyway, still looks bad. But I hope you understand the fundamental principle, okay? Whenever when we talk about the phase diagram, the closed system, the G is a function of the P and T. So basically, it is a 3-dimensional object. And the distribution of G is the 2-dimensional plane, okay? Whenever two-dimensional planes get cross each other, we have the phase boundary, okay? We have the phase boundary, okay? We have one phase boundary, the other phase boundary, and 3, 1, okay? But think about in the space, you have 3 planes. You have 2 planes crossing that way. You have another plane. You have another plane. You have 2 planes crossing that way. You have another third plane come to this one. And you can, you have 1, 2, 3, totally 3 cross lines. And all cross lines will go through the single point, okay? And that single point is a triple point, right? No matter what's the orientation of the point, you can always find this point. If in my annual review or my evaluation, I see any student complain, really bad hand drawing, I'm okay with it. But I'm trying my best to explain. But anyway, so let's put in the homework. So everybody try their best to draw a good picture. And then the best one I'm going to use for my class for next time. Probably the better exercise is with 3D print. Right? We can 3D print.
See the inside.
You can see the inside. You can see the 3D objects, right? No. You just print the post as the post we have and print plane.
But you cannot have planes like intersecting each other.
What's that?
Can you have planes intersecting each other?
Yeah, why not?
Oh.
Build a 3D model, okay? So this is probably you can do as a project. Give me a second. So whenever you can print it out, I can give you some extra credit for the class.
That answered my question.
What's that?
That answered my question.
Oh, yeah. You have credit, of course.
But if we try, we try and cover.
Huh?
If we try, it maybe it wouldn't look very nice, but we tried. Would you give us extra credit?
Oh, if you have give me one piece, I can give you a full credit. But if not, we can give you half credit.
Okay.
Okay. Online student, I know that you cannot deliver the hard copy, but if you can give me a good 3-dimensional model for us to print it out, I can also give you the credit. Okay. Everybody can try. As long as you try, I can give you some credit. So this can be part of homework. Actual homework. Oh. Anyway, so we're going to move on to the next chapter. The next chapter is called what? What's the name of the next chapter on the textbook? I forgot. Anyway, it's called the thermodynamics of the gas or whatever. Anyway, so we're going not necessarily for us to mention about them. Okay? We're going to talk about the mixture of. First of all, we talk about mixture of ideal gas. Okay. Of ideal gases. The first concept we're going to mention is we call it the Dalton. Dalton's law of partial pressure. Okay? What does that mean? Remember, right now we're talking about ideal gas. So at the beginning, we mentioned ideal gas means these basically particles, okay? The single mono atom particles has no interaction to each other. They just randomly move, okay? They have no attractive or repulsive interaction to each other. They can only have a collision to each other and scatter away. So as long as they touch each other, they can slide with each other. Otherwise, there's no interaction, okay? In that case, so if we mix a lot of the single particles, different type of gases together, they are still ideal gas. They are still ideal gas. There's no interaction to each other. We are not the chemical reaction yet, okay? There's no reaction, just mix helium with the argon or helium with neon or whatever, okay? That ideal gas. So in that case, remember we have the PV equals to nRT. So this is the equation of ideal gas, right? And N here is the total, the mole number of the gas, okay? That means this one equals to sigma I, Ni, Ri, RT, okay? Ni is what? I is what? I labels different kind of atoms, okay? Oxygen, nitrogen, helium, neon, argon, you name it, okay? And then the Dalton's law of particle pressure tells us the P equals to sigma I Pi, okay? And Pi is what? Pi, we call is the partial pressure of gas I, okay? Of gas I. What does that mean? What does that mean? It means something like this. It means something like this. So consider we have a tank. We have a tank. The volume is fixed. The volume is fixed. Okay? And at the beginning, we add gas, this type of gas. Okay? And this one is the gas gas 1, okay? And then this one is a P1. Okay? The volume is V, of course, and the T. Okay? And now, I have another tank of gas. The same volume, but different type of gas. Okay? Gas 2 and the P2. The volume is still V and the T. Okay? And we have third gas. Okay, triangular gas. P3, V, P. Okay, so we have 3 independent tanks. Right now, we take all the gas away from the tank and mix them together in a single tank. Still, the tank has volume of V. Okay, but right now the gas are mixed to each other. Okay? Got the picture? Understand the process? We have 3 gases. All of them have a volume of V and under temperature of P and T. Okay, one gas has the pressure of P1, P2, and P3. And then if we mix them together in the tank with the same volume and the same temperature, then the P simply equals to P1 plus P2 plus P3. Okay, that means we can add the volume together, the pressure together. And each pressure, the pressure of each component is called the partial pressure of the gas. Okay?
Almost made it.
The partial pressure of the partial pressure of the gas. If you want, you can put some YouTube video online. I mean, as long as UCF do not complain about the copyrights. I don't mind. I can get some actual income from YouTube. You can say, oh, this is the best thermodynamic class across the United States. All right, anyway. So then why is like this? Why is like this? It's still the same thing. There's no interaction between gas, okay, among each other. But if they have an interaction, it's not the case anymore, okay? It's not the case anymore, okay? So this one, basically, we call it the Dalton, right? Dalton? Yeah, pronounce it Dalton, okay. Dalton's law of particle pressure. only work perfectly for ideal gas. Okay, if for the real gas, not the case. Okay, but if the gas have reaction, it's another story. Okay, you mix the hydrogen and oxygen together, it becomes water. Okay, it's not gas anymore. Okay, so we put this equation together, and then what do we have? We will have sigma I pi v equals to sigma I ni RT, and then we have pi equals to ni. Okay? And we have this kind of relationship for each of the components in the mixture. Okay, we have this relation for each of the components in the mixture. And the partial pressure times the total volume equals to the mole number of the specific component times RT. Okay? Because every type of gas share the same temperature and volume because they share the same room. Okay, they share the same room. Okay, so this one we call is Dalton law of particle pressure. Basically, this is experimental observation. Okay, this is experimental observation and works beautifully for the ideal gas. Okay, but if the real gas start to deviate from this kind of relationship. Okay, question? Okay, if there are no questions, we will move on to the next thing. Okay. The reason we talk about this Dalton's law of partial pressure is because we want to use that one to derive the Gibbs free energy of the mixture. Okay. So we just the copies here. It's called Dalton law. Okay. So basically, the total pressure equals to sigma I pi and pi. Who is leaving?
The ghost.
I hope there's a ghost in the world. At least after I pass away, I still can have something to do. To scare you guys. And I will have a busy season during the Halloween. I will become special guest. We find some real ghost. That's what give him welcome him to show up. Okay, so we're going to talk about second topic. It's called the Gibbs free energy of ideal gas mixture. Okay. To talk about that one first, we need to know what's the definition of the free energy of the mixed system, dG equals to T minus S dt plus V dP and plus what? Sigma I, right? Mu I. What? Mu I is function of what? Mu I is a function of T and P, right? We have a question mark here, okay? What is function of P, okay? And D N. Okay? Do you remember the definition of chemical potential? The chemical potential, that means partial G, partial N, I, okay, as a constant T and P. Okay, so this is the definition of the chemical potential. Basically, that is the free energy, the hold by the free energy of 1 mole of the ideal gas. Okay, that is the definition. Okay, so the question is, okay, so you can see that we already know the partial, this one, right? We already know this kind of Dalton partial pressure. We can change this one a little bit more. question is that can we do that? Can we do that? Okay. The question is whether the chemical potential of the UI of the I gas only depends on Pi, or it depends on the hole pressure. Okay, that's the question. The question is, let me, is whether what's the correct grammar? Whether does mu depend or whether mu depends? I need to add the does there?
No, it does.
Whether mu I only depends on Pi or P. I think this grammar issue have some grammar issue, right? What's the right expression?
That's right.
It's good?
Yeah.
Whether you either.
If I have a question mark, it should have something here. Does, is, whatever.
Whether or
Well,
not.
if you, okay,
No.
you get rid of whether, and then you could say, does
Yeah.
UI only depend on it? Then you
Good
put a
point.
question. Look at us. Look at us go.
Does. Okay, I will pay tuition. Does mu I only depends on Pi or P? Okay? That's the question. Okay? If it depends on P, that means it also depends on the pressure of other gases. Right? If it only depends on Pi, then the job is easier. Okay? That's the question we're going to answer. Okay? Let me that's the question. Okay? Okay, now right now let's consider the following scenario, okay? Right now we have a tank. And in the middle, we have a membrane, okay? We have a membrane. It's a very special membrane, okay? It's the membrane. Okay? It's only allow one type of gas to penetrate, to go through it freely, but block the other one. Okay, this membrane indeed exists, okay? For example, for most of metal, if you have a piece of metal, you just make the metal into film. Most of the time, hydrogen can go through it, okay? But nitrogen cannot, okay? The reason is hydrogen is so small, it can penetrate anything. That's the reason hydrogen is very dangerous. I mean, there's kind of phenomenon, this is your material science, but if you talk with probably the mechanical engineering department, know better. The steel, they have the phenomenon, we call it hydrogen brittle or something like that. That means the steel exposed to the hydrogen eventually got cracked and got the structure got broken because the hydrogen goes to it, once we penetrate through it, okay? This membrane indeed exists. Okay, so let's consider in this part we have a mixture of gas. Okay? And in this one, we only have one type of gas. We only have one type of gas, okay? This one is pure gas, this one is mixture. Okay? And of course, the NJ can go through it freely. Okay? This can go through it freely. Got my point? And under the thermal equilibrium, okay, under the thermal equilibrium, the dG equals what? The change of the total Gibbs free energy. For example, equals to what? Should equals to this one, right? Should equals to mu J. Let's see this one. Is mu J, and in this one is we call it the mu J mixture. Okay. Okay, we can call this one is the mu J simple. Okay, this is the mu J mixture. That is the mu J mixture. D and J. Correct? If we have a number of particles of D and G go through, exchange through the membrane, okay, then the change of total Gibbs free energy should equal to this. Correct? Is that true? Right? Because I mean, when the liquid, sorry, not the liquid, when the gas, I mean the diffuse from this part to this part, okay, then we have mu Gs increase and mu Gm decrease. Not decrease. The total free energy increase on this end is mu Gs times dng, and decrease on this side is mu Gm divided dpmg, but with a negative sign, right? Then the total change of the free energy of the system equal to this expression. But under equilibrium, we should have this one equals to 0. Correct? That's the definition of equilibrium, because everything reach the minimum value. Then we have the minimum, right? Then this one will tell you the mu Gs equals to mu Gm. Okay, that means the chemical potential of the gas, no matter whether it's a single component or mixture, the chemical potential should be the same. Should be the same. Okay, everybody? Should be the same.
Does the I include a J on the right
No,
side?
I'm only talking about, yeah, I only include the J. Yeah. Yeah, include the J. You can change the J to 1, 2, 3, 4, 5. Okay? And I is from 1 to 3, 1, 2, 3, 4, 5. Anyway. Any question here? No question, okay? So what's the mu J? And what's on this end? We know that mu Js should be be a function of temperature and PJ S, correct? And on this end, the mu Gm is the temperature of T, and also some pressure here, okay? Something here. But we know that it's the some pressure, okay? A kind of pressure. Let me, it's a pressure, right? Okay, it's a pressure. Any type of pressure. Okay? But we know for the system, we only have 2 degrees of freedom. Correct, everybody? For the gas, we only have 2 degrees of freedom. If the chemical potential equal to each other and temperature equal to each other, then the pressure must be equal to each other. Correct, everybody? But we know, you know, the pressure on these two ends is definitely different, right? This is a mixture, this is a single one, right? And then this one, then in other words, even inside the mixture, the pressure is still equals to the PGS, right? Even the mixture is still equals to PGS, right? In other words, the PGM equals to PGS. Okay? That means the pressure only decided by the partial pressure of this gas instead of the pressure of the entire system. Follow my point? In other words, we can use this expression. Okay? The chemical potential of a component only depends on the partial pressure of it instead of the total pressure. Okay? For example, in a tank, okay? Originally, this tank is filled with nitrogen, okay? And then I start to put oxygen into it. Of course, the pressure goes up, but the chemical potential of nitrogen doesn't change, okay? Because it's defined by the partial pressure of the nitrogen. Got the point? What's the reason for that? Because there's no interaction. There's no interaction, okay? There's no interaction. Okay, right now we know this one. This is very important, conclusion, okay? And from this one, make the job easier. So that means if it only depends on the partial pressure of the system, we can calculate the chemical potential of each atom, each type of gas individually, right? Of each of the gas individually. We do not need to consider there's no interaction. We do not need to consider the interference or influence from other type of gases. Correct, everybody? So what's the definition of the mu J, of mu I? Mu I basically is the Gibbs free energy of 1 mole of the atoms. Correct, everybody? Is that right? Then the B mu J should equal to what? Should equal to, forget about it. We know that the J equals to dJ equals to what? Equals to minus S dt plus VdV. Okay? Because right now we do not consider temperature fluctuation. Okay, we are dealing with the problem under the constant temperature, then we can remove the effect of this term. Right? Just lower it, right? We only need to consider this one. The same thing for 1 mole of the ideal gas. It becomes, this one is J molar volume. Correct? The M here means the molar volume. Right? And this one is ideal gas is equals to what? Equals to RT times PJ. Correct? And then this one equals to RT. And then we have the mu J equals to mu J non plus RT times log PJ. This is just the integration constant. Okay, we don't need to worry too much about what's the value of it. Okay, that's not very critical. Okay, we have this expression. Okay, and then what about the free energy? Total free energy of the gas J should equals to Nj mu J, right? And equals to Nj mu J non plus Nj RT log Pj. Correct? That's the Gibbs free energy of one type of gas. And then what's the total gas? What's the total free energy of the gas? The total free energy of gas simply equals to sigma I Ni Ji. Ni mu I. Mu I. This one equals to G non plus sigma I Ni RT. Okay. Questions, comments, problems, issues, unclear, confusion? Everybody understand what I'm saying, right? If you believe I make myself understood, please say, yeah. If you do not believe what I'm saying, please say, yeah. What's your response? You cannot keep silent, okay? What's your response?
Try to figure it out a long time, I guess.
Yes, yeah.
Okay. Oh, by the way, do you know why when do the voting people say not say yes or no, but say yeah or nay? Right? Do you know what's the reason for that? For example, I agree. I don't say yes, but I say yeah. But if I don't agree, I say nay, right? What's the reason for that? The reason is when you say yes or no, there's confusion. The reason, for example, if you ask me, oh, you haven't had your lunch, right? I say yes. That means I already have my lunch, right? Yes, I did. Or no, I didn't. But yes does not mean yes means I confirm I have lunch, but does not mean I agree with what I'm saying. Basically, my response is disagree with what I'm saying. You haven't had lunch. Yes, I have my lunch. Right? You cannot say no. I already have my lunch. Okay, so you have this kind of confusion. But if I say yeah, that means I agree with what I'm saying. I have not had my lunch yet. Okay, it's just this is. I mean, when you go to the Department of Voting in the whatever. In the future, probably somebody of you go to the Congress, you will know this kind of very interesting. Anyway, everybody understand what I'm saying right now, right? Okay, so we're going to keep moving. All right, so remember what is the PI? We know that the PI, we know this equation, right? And we also know this equation, right? Right? This is from the Dalton's law, right? And then from these two equations, what we will have is this. The PI simply equals to Ni, sigma I, Ni. Let's change to J. Okay. I don't want to use I that much. And this one is simply the fraction. We define this is a fraction of the J component inside the gas. Okay, that means the fraction, the ratio. Okay. And then by using that, we can further change this expression. Ni log P plus RT on X I. That's a Gibbs free energy. Okay. Questions, comments, issues, problems? Okay, so, question. This is the mixed gas, okay, this is the mixed gas. Right now, consider we have a tank of gas. Total particle number of N, the more number is N, okay, the pressure is P. And we only have a single type of gas inside the tank. So what is the Gibbs free energy of this gas? Simply equals to nRT times log P. Correct? And of course you know this term. We know this term. This basically is just the total molar number. So that means for the mixed gas, we have one extra term. Right? We have one extra term.
What is X supposed to mean?
X is the ratio of the i's item inside, the percentage. Okay? That the xi is defined by the number of I particles divided by the total. That is the ratio of that atom inside the mixture. Okay? Fraction. Okay. What's the reason for that? Why we have this term? Basically, this term, you can see that this xi always smaller than 1. It's always smaller than 1. Correct, everybody? Then this term is always negative, right? That means for the mixture, compare with the pure gas, with the same pressure and volume temperature, the mixture has lower total Gibbs free energy because of this term. Okay, so where does this term come from? This term actually comes from the, we'll mix the gas. You increase the entropy. Okay, it becomes more chaotic, right? Let me give you a very simple example to show you why it's linked to the, why it's because of the entropy. We can just calculate, okay? We know that the G basically is the equals to ST, right? We have this term, N plus and P. Don't do that. This is W. DG equals the minus ST plus. Okay? You know that one. And you can see this term has no relation with P, right? So this one only depends on temperature. Right? This one only depends on temperature. So this one is corresponding to this term. Correct, everybody? This one has no function, it's not function of P anymore. This part is function of P, so it's corresponding to this term. This one has no function of P, so it's only corresponding to this term. Right? And we know that through the integration, we know that dg, okay? And of course we plus constant. Then we can see from that one, we know the change, the delta S, should equals to delta G divided by T. And this part is delta G, right? And this one is 2. Minus, okay, we have negative sign. Then I R log xi. Okay? And you can see the xi lower than 1. This term is negative, but this one is positive. That means the change of the entropy is large. It's positive, right? So this is the preferred and spontaneous process. Okay? And to prove it, we can do something like this. Okay, we can do one experiment, mental experiment, to verify this expression. To verify, when you mix two types of gas, that's the change of the entropy. We have a tank. First of all, at the beginning, we separate this container into two chambers. Okay, this is gas 1, this is gas 2. Okay, this is gas 1, gas 2. Okay, so remember what's the definition? What is the definition of the, what's the definition of the, give me a second. This is the 1 mole of gas 1. This is the 1 mole of gas 2. Okay. Remember the definition of the entropy? Is the R times log omega. Okay. Omega is what? Is the number of the microscopic state corresponding to the, the microscopic distribution, right? Right, this one. Okay, then suddenly we remove the separation, and then these two gas start to diffuse to each other, right? And eventually we have gas 1 from remove, gas 1 originally occupied only half of the tank, but right now it's occupied the entire tank, right? Correct, everybody? Originally, gas 1 only occupied half of it, but right now it's occupied the entire tank. So, how the total microscopic state change? The microscopic change doubled, right? Exactly doubled, right? So then the S1 equals to R ln 2. Double, right? Same thing. And the total change, 2 times R ln 2. Correct, everybody? And right now, you know the final state is what? Is the whole tank of the mixture of the I and 2, right? Look at this equation. This one is 1 mole of the gas 1, R ln, right? X1 is half, right? And also we have negative sign, negative. 1 mole times R ln another half, correct? So this one equals 2 times R ln 2. Okay? There's no minus. It's positive because I already have negative sign here. Okay? That's the reason. Okay? This means if we have the mixture of gas, the entropy also change. Okay? But on the other hand, it also tells us that term only got contributed by entropy. There's no energy difference. If you mix the two gas together, the energy or the enthalpy doesn't change, but only the entropy change. Okay? Because it becomes more chaotic. Questions, comments? All right, so exercise time. Let's do some exercise. Okay, everybody stand up and do some push-ups. It's a CL. E-X-E-R, C-A-S-E, or S-I-C-E.
C-A-S.
This is how AI ruined my memory. Okay, we're going to give you a very simple explanation about osmotic pressure. Do you know what is osmotic pressure? Okay, right now consider this one. So we have a U-shaped tube. We have a U-shaped tube, okay? We do not fill gas, we fill the liquid, okay? But right now, let's assume the liquid also follows the law of ideal gas, okay? Although it's liquid, but it's still ideal liquid. PV equals 1 RT, okay? Let's assume that, make the job easier. In the bottom, we have a membrane, okay? The membrane is transparent to water, okay? But it's blocked, salt, okay? You know what is salt, right? Sodium chloride, okay? So then on this part, we put the same amount of water and salt water. Okay? And the percentage, the molar percentage of the sodium chloride inside the solid water is N divided by the sigma divided by N H2O plus N. This one we can call it the SX, okay? It's much smaller. It doesn't matter, we just make it worse. It doesn't matter actually, we just So at the beginning, the water and the salt water share the same level, okay? And what's the phenomenon? If we keep it for extended time, for probably for 1 day, what will happen?
From left side, water will go to the right.
Huh? Diffusion. So
Even out.
how it works?
Concentration gradient is there,
Kind of gradient is there, but
so it will try to balance.
yeah. Then what?
Then from the left side to the right side, water will pass slowly.
Water will go from the right side to the left side,
From left to right.
to the left to the right. What's the reason for that?
To dilute the sodium chloride.
Huh?
To make dilution of the sodium chloride.
Why is it have this trend to make the solution more diluted?
To attain the equilibrium of the concentration.
I know, but thermodynamic point of view.
More microstates.
Huh?
More microstates.
The what?
More microstates.
More microstates? Yeah, that's true. Yeah, that's is more fundamental. That's so fundamental. Yeah, exactly. More. I mean, basically, it's driven by the entropy. Okay. If the more will come, there's to make the system more chaotic, right? The reason is, remember, on this one, we just treat the salt. Although it's really ridiculous, but that makes the job simpler. Okay. This is the gas. We call it water gas. This one is the water and the sodium dichloride. Sodium gas. Okay, we just assume it's gas. Okay? Oh my goodness, what I'm talking about. Anyway, so we just assume it's gas. Okay. So at the beginning, we see that the pressure here is the same, right? The pressure here is the same. That's the reason I'm saying this one is very small and one doesn't change the density of water too much. So here, the pressure is the same, right? But if the pressure here is the same, then the partial pressure of the water here, should equals to what? 1 minus XS times P, correct? The partial pressure of water on this end is lower than the pressure of water on this end. Correct, everybody? Is that true? Right? And then we know that chemical potential is a function of P and T. Then the chemical potential on this end is larger than the chemical potential than the right hand side, right?
So the chemical potential basically driven push this kind of diffusion happen. That's the reason we call it chemical potential, because it tells us any kind of the chemical reaction or any kind of reaction. It's a potential. Okay? Basically, it's more like a potential energy. Okay, its potential is higher. It's driven the driven the evolution to the direction to lower the chemical potential. Right? That's the reason we call it potential. Right? That's the reason. That's how the diffusion can happen. It's not called diffusion. It's called
Osmosis.
what's that?
Osmosis.
Thank you. That process. Okay. Okay. Right now, everybody understands.
The chemical potential on the left is higher because the partial pressure of water on the left is higher?
Yeah. Okay, right now, let us calculate, okay, do some calculation. We know that because driven by the difference of chemical potential of the liquid or the partial pressure difference from left to the right side, calculate, we know that the liquid goes from this end, right? So this is water, this one is salt water. Okay? Right now, calculate the height. Different height, okay? And we can make the job easier. We assume the water from the top of the pure water to the bottom, the height is h, the capital H. Okay? We calculate the difference between these two water level, the surface levels. Once again, the concentration of the sodium chloride inside water is very slow, or it's very low. Okay, it doesn't change the density significantly. Okay, we just assume the water on the right hand side and left hand side share the same density. Okay, to make the job easier. Huh?
What to calculate?
You just calculate delta H. Express, or like the be more precisely, express delta H in terms of H and excess. Okay, and of course we know the density of the water is the rho H2O. Okay, that's the density of water. And today in the dining hall, I was waiting, and there's another person besides me. So just to say hello, just say how are you doing? I don't know the person. And you know what they say? Wow, your gray hair looks good. Seriously? You know, I'm just thinking which one is better. Just to dye them all into the black, or just to bleach all into white. I don't know which one looks better. You give me suggestions. Okay? But if you give me the wrong direction, you lose the credit. But I know that the entropy of my hair right now is pretty large. I want to lower it. That's the reason I told you, right? If you want to lower the entropy, you need to spend energy or money. You need to buy the dye, or you need to buy the bleach. have a colleague, a good friend, and one time he just colored his hair. His hair out purely white, silver color, and he bought some dye from grocery. It's expired, but he did not notice. After dyeing the color, all the hair turned blue. And, oh my goodness, I need to attend the meeting. I mean, it's a conference in the DC. How could I see the program manager? But it turned out he's become very impressive. Everybody know him. Oh, the blue guy. And I also make myself very famous in the Department of Defense. I went to the Department of Defense meeting last month. Yeah, last month. And before the annual meeting, everyone knows me. Do you know how? Because at the end of first day, they make an announcement. Hey, Dr. Sidon Lei, please come to the front desk. You lose your credit card. And the credit card, my picture on it. It's a Costco credit card. I have a picture on it. And everybody know me. And the second day, when I see the program manager and also some other professor from university, what's your name? I said, oh, you're the guy who lost a credit card yesterday. Yes, I am.
How did you lose it?
It's just in my pocket when I take the phone, whatever, it dropped down.
Is that just like have it loose in there, or
What's that?
is it just like loose in your pocket? You have a wallet?
Yeah. I don't have wallet. I don't have
Interesting
wallet.
choice.
Yeah. You can see that I don't have my wallet. All my card or whatever, ID card, whatever is here.
Oh, sorry.
Yeah. And the good thing is that I have my ID here, so when I want to swipe into the door, I just put my cell phone there. And one day, there's another guy following me and said, hey, how do you make your cell phone store the information in the car and open the door? I don't have. This is a secret. I have pocket with it. But sometimes when I take my ID out, the credit card just suddenly dropped down, but I did not notice. But anyway, let's go back to this. Okay, so we know that eventually, under the equilibrium states, the water on the left-hand side and the right-hand side should share the same chemical potential, right? And we already know the chemical potential is the function of the partial pressure and the T, right? And we know that on the right and on both sides they share the same temperature, right? And the chemical potential would be the same as well, right? Then the partial pressure should be the same, right? The partial pressure should be the same. Okay. After doing that, we can do something like this. So on the left-hand side, the pressure here, okay? The pressure of the water here is what? It's the intensity of water times the gravity, whatever, times the height. Correct, everybody? Right-hand side, the bottom is the water plus equals to rho g times h plus delta h. Correct? I think you know this expression, right? Correct, everybody? And this one, that's the pressure, right? But we know this pressure has two components, right? Equals to what? Equals to, one is from the water, the other is from the salt. Again, we just treat them as ideal gas. Okay? Although, don't worry how ridiculous it is. I just assume you are drinking gas every day. Okay? Okay, so then this one equals to P2O. Partial pressure, okay? The partial pressure, we know that the PH2O, so this one equals to 1 minus XS, XS. Correct, everybody? This is the ratio, right? And then this one equals to PH2O times, what's that? I think my brain stopped working. correct? And then this one equals to 1 minus xs. Is that correct? Okay. Then we know that rho times J times H plus delta H should equals to P H2O divided 1 minus XX. And the PHO given by that one, 0 GH 1 minus SS, right? And of course, we don't need to worry about this two term anymore. Okay. And similarly, H plus delta H equals to H minus SS. Okay? And you can do the following calculation. You will know what is delta. Okay. And you can see we have the different, the liquid on both ends do not share the same level anymore. So we have the pressure difference here, right? We have the pressure difference. The pressure difference